Let's talk for a second about the formalism behind how it is that you describe an acid-base reaction. I told you that there is this sort of vocabulary that we're going to want to use to describe it, and it gets pretty sophisticated coming forward. But for right now, understand that what we're primarily interested in when we look at an acid is this thing of the form HA, where this thing on the left here is the proton that's going to be dissociated in this classic sort of Bronsted acid notion. And when it dissociates, it's going to make some protons and some A minus. Well, there's a word we actually use to describe HA relative to A minus. This is an acid-base pair that's conjugate. The conjugate acid and the conjugate base, they differ by a proton here. And there you see, in fact, that difference of a proton. So that's the acid, that's its conjugate base, and that's the proton. We can immediately set up an equilibrium expression for this, which is a K value, which is equal to the H plus times the A minus over the HA. Notice that as I set this thing up, very sadly, this HA, this acid, actually goes into solution. It is not a solid that falls to the bottom of the beaker. We immediately see that as a result, we do not have as simple a case as we do with the soluble salts. With the insoluble salts, excuse me. When those things go into solution, they fall to the bottom as a solid, which means that their activity is 1, which means that we can ignore it. And then you have a very simple kind of relationship here with only the stuff in the numerator that matters. With acids and bases, that goes into solution. It's a real live concentration I have to take into account, and consequently the math becomes more challenging. It's why it is that we wait until after we do the salts before we take a look at the acids and the bases. But this is the formalism we set up to describe an acid dissociating in water. It's written as a dissociation, and it produces this equilibrium right here. And in the same way that we write KSP to tell us that we have a solubility product equilibrium as a general form, we write a Ka to suggest that we have an acid dissociation. How do we know it's an acid dissociation? It's always producing a proton. Well, what can we talk about an equivalent version of this when we're looking at bases? Yes, in a base, and I'll write B for my base here, I can have a reaction take place in which, in the presence of water, I can make a BH plus and an OH minus. Now, we look at this, and it doesn't appear to be as intuitively obvious as this case up here, because it involves water, the solvent. But notice that water, the solvent, is providing a proton that's going to be attracted to the base, and that what's left over is a hydroxide. What makes this a base, then, is the fact that hydroxide is produced in the reaction, as opposed to a proton being produced in the reaction. We can write down the K for this. It's the BH plus times the OH minus, and again, the base goes into solution typically. And so we have a ratio with a denominator, but this is the basic equilibrium in the same way the Ka describes the acid, the Kb describes the base. So these are the two forms that we're going to be using for our acid-base equilibria. The acid form, the basic form. How often do we use these? Always. It never varies. They're always written as dissociations. If it's acid, it makes the proton. If it's base, it makes the hydroxide. What is it that we want to be able to measure in all of this with the Rice expression? Typically, we either want to measure the amount of proton, if it's an acid, or the amount of base, hydroxide, if we're doing a reaction in base. We end up being able to calculate a pH. This amount here is minus the log of this amount here, or a pOH as the amount of the hydroxide.